I don't see you, Chris.
I'm gonna join.
Okay. So let's start. We looked at the capacitor last lecture. Today we're looking at the inductor with the letter L for the Henry. And we said that the inductor, which consists of a coil of conducting wire, is a passive and stores energy in the form of a magnetic field. So it's an energy storage element. Definitions, we did that last. Looked at how the inductance L is affected by the physical structure of that coil. And this is the voltage current relationship of the inductor. So V across an inductor, if there's an inductor that carries a current I, V is going to be equal to L di dt. Okay. Now we have here a simple example. So L is 0.1 and I of t equals 10t e to the negative 5t amps across the inductor. Okay, so t equals L di. L, it's going to be 0.1, we're going to put that later. D by dt, 10 to the minus 5t. So that's equal to L is 0.1, and the 10 that you have here. I'm going to bring that outside, and then d by dt e to the. Okay? So that's equal to 10 times 0.1, and then I have to find this one, the d by dt, sorry, t times e to the negative 5t. So that's equal to e, the negative 5t, that's the derivative of t, dt, that's 1 times e to the negative 5t, plus, keep the t, and find the derivative of this one, e to the negative 5t, that's e to the negative 5t multiplied by minus 5. Okay? So we have here e to the negative 5t minus 5t e to the negative 5t, right? So that's the voltage. Okay, across your inductor. You can rewrite it as 1 minus 5t e to the negative 5t. So again, there's a bit of math involved, and we saw in the capacitor how I equals C dV dt. For inductor, V is equal to L di dt. We have some important notes, and they're going to echo what we said already concerning the capacitor. But whatever current is going to relate to the inductor's voltage, and whatever concern the capacitor's voltage is going to relate to the inductor's current. It all comes from these voltage current relationships. So the first note here, if the current I through the inductor is 0, now look at that. Okay, we know that V is equal to L di dt. If the current is constant, if the current I is constant, then di dt is 0 and the voltage is 0. Okay, so regardless of the value of the current flowing through that inductor, if it's a constant, you don't get a voltage. It has to be a changing current, like this example that we had on the screen here. you had a changing current. So I of t was equal to 10t e to the minus 5t. So the current is a function of time. And therefore, you can find di dt for that. And you can find the voltage. But if your current is a constant, then your inductor is not going to produce any voltage across it. And V is equal to 0. So the inductor practically behaves like a short circuit if you have a constant current flowing through it. Okay? If the current is constant, it becomes like a short circuit. So the capacitor behaves like an open circuit. If you have DC conditions, the inductor behaves like a short circuit. And the second thing that we derive from here is that cannot change inductor. So then instantly a totally different value. The current during that time is going to be vertical. So di dt would be infinity, and you cannot have that. So the current can never have a discontinuity, and that is to parallel whatever we said for the voltage in a capacitor. In a capacitor, the voltage cannot jump instantaneously, and in the inductor, the current cannot change instantaneously, because that would mean that the voltage would have to go to infinity. Okay? So you can deduce all of that from this voltage-current relationship. V equals L di dt tells you everything. Now, if you want to find in an inductor the current in terms of the voltage, same thing that we did for the capacitor, really. Okay, you're going to have this equation. I is equal to 1 over L integral from t naught to t, V of tau d tau plus I of t naught, and that is the current through the inductor at time t equals t naught. We call that an initial current. So we would say if you have an initial current flowing through your inductor, it means there is an initial voltage there. Okay. Sorry, if you have an initial current, it means there is initial energy there because the current produces the magnetic field. And if you have a voltage that is changing across it, it produces a new current, which is 1 over L integral V of tau d tau. So the total current I is going to be the newly produced current because of the varying voltage plus whatever initial current was there. Okay. Find the current voltage across it is given. Assume that I at t equals 0, which is I of t naught, that's equal to 0. So don't have an initial current in this particular example. So what do I have? V of t if t is less than 0, that's equal to 0. There's no voltage. And then I have this function here, 30 t squared, for t greater than 0. Okay, that's the value of your voltage. So to find the current, I of t is equal to 1 over L integral from 0 to t V of tau d tau plus I of t, I at t equals 0, or I of t naught. Now this one, it's given as 0. So here we have 1 over L, integrate from 0 to t. Well, before 0, that's what I'm saying from 0, because before 0 there's nothing. And then you have here 30 t tau square d tau. Okay? So the 30 can come out here from 0 to t tau square d tau. If you want to integrate tau squared d tau, That's tau cubed over 3, right? And the limits are from 0 to t. That gives you 10 over L t squared. We have a 5 Henry inductor. So that's equal to 2 t squared amps. T cubed, sorry. Cube. Not harder than this. That's probably the hardest you're going to find. I at minus infinity to I of t. Okay. We're going to be doing the integral here. So I di becomes half I squared, and I have the L. These are inductor, and therefore I being the current at any going through your inductor, there's going to the energy, and find these values of current I That's 4 joules. Okay. Any questions? Now, what do we do when we have inductors in series? We have a derivation here. You have a set of inductors, L1, L2, L3, they're all in series together. And you have, because they're in series, so it's the same current flowing through all of them, which is this current I. And each one will have a different voltage developed across it. So you have V1, V2, V3. If you do a KVL, then the total V is equal to the sum of those voltages. V is equal to V1 plus V2 plus V3 all the way up to Vn. And each one of those voltages can be written like this. So V1 is L1 di dt, V2 is L2 di dt. So di dt is really a factor. So you can take L1 plus L2 plus L3 and so forth all the way up to Ln as a common bracket multiplied by di dt. Okay, and if you equate that with the right-hand side, which shows us a different inductor, L equivalent, the voltage V would be L equivalent di dt. So that just tells us that L equivalent, the equivalent inductor of a set of series connected inductors, is equal to the sum of them. So L equivalent is equal to L1 plus L2 plus L3 all the way up to plus Ln. So inductors in series, they add up, their values add up, exactly like resistors. Okay, and you have to notice that the capacitor, if you remember, behaved differently. When we had capacitors in series, you could not add up their values. So inductors really, as far as the equation is concerned, we deal with it like we deal with resistors. Okay, what happens with inductors in parallel? I have here a number of inductors in parallel, L1, L2, L3, all the way up to Ln. We have one voltage across them all because they're in parallel, but we have a number of different currents, I1, I2, I3, and the total current I is the sum of all these currents. I equals I1 plus I2 and so forth. And again, you're going to use those equations here. I1 is equal to 1 over L1 integral from T0 to T v dt plus the initial current. And you do the same for all of them. When you add them all up, you end up having this result at the end. That 1 over L equivalent is equal to 1 over L1 plus 1 over L2 plus 1 over L3. Now the initial current that is flowing, if you have a number of parallel connected inductors and each one has initial current, then that would be equivalent to one equivalent inductor and with an initial current that's equal to the algebraic sum of all those initial currents that were flowing in there. But as far as the equivalent value of L, so L equivalent is 1 over L1 plus 1 over L2. So again, the inductor here, as far as the equation goes, looks like the equation of your resistor. Okay? And I mentioned that the initial current is equal to the algebraic sum of the initial currents that you have. Okay. Special case for only two inductors in parallel. Again, we did that before. If you only have two inductors, L1 and L2, so L equivalent is going to be equal to L1, L2 over L1 plus L2 product over sum. So again, inductors in parallel, you use an equation that reminds us of the equation that we use for resistors in parallel. I have a table here. And in this table, I put all of the results that we had. I'm comparing here the voltage current relationship and the current voltage relationship and all the other things, power and energy and how you combine them, series and parallel and so forth. I'm putting in this table I'm comparing resistors with capacitors with inductors. So on the top line, how much is the voltage if you're given the current? So for a resistor, V equals IR. For the capacitor, V equals 1 over C integral T naught to T I of tau d tau plus V of T naught. For the inductor, V equals L di dt. Now, if you're given the voltage, if I want to find the current, so for the resistor, I equals V over R, capacitor, I equals C dV dt. For the inductor, I equals 1 over L, and you have the integral. Now, what is the value of power in a resistor? Now, typically for a resistor, we look at the power. That's the easy equation that we deal with, I squared R or V squared over R. That's power in a resistor. For an inductor or capacitor, we kind of tend to look at energy. And we have the energy equation for a capacitor. That's half CV squared. And the energy equation for the inductor is half Li squared. How do you combine elements in series? If they're resistors, R1 plus R2. Same thing for inductors on the far right, or L1 plus L2. But if you have capacitors in series, two capacitors in series, that's C1, C2 over C1 plus C2. That's a review. If you have parallel elements, we know that two parallel resistors, R1 and R2 in parallel, you get the equivalent R1, R2 over R1 plus R2. For capacitors, if you have two capacitors connected in parallel, you add them up, C1 plus C2. For the inductor, the equation looks like the resistor equation. Now, how does a resistor behave if you only have DC as opposed to having, maybe sources that have a time dependence? So for the resistor, it doesn't matter. The resistor is always a resistor. It behaves the same equation, same Ohm's law, regardless of what time the capacitor behaves as an open circuit, and the inductor behaves like a short circuit. Now again, the circuit variable that cannot change abruptly. Okay, we saw that we have issues with capacitors and inductors with voltage or current changing instantaneously. You don't have any problems with a resistor. Resistor doesn't have any restrictions on that. It's not applicable. Ohm's law is Ohm's law. If any of the voltage or current just changes that instantaneously, the other one follows instantaneously. You don't have any problems there. But because of the dV/dt part of the capacitor equation or di dt part of the inductor equation, then we have some limitations here. So for the capacitor, the voltage cannot change instantaneously. Otherwise, dV/dt would go to infinity, and that cannot happen. And for the inductor, it's the current value. The current cannot change instantaneously in an inductor. Okay, so you have to keep that in mind. Find the equivalent inductance of the circuit shown. We have a circuit with a number of inductors connected. We want to find what is the value of, the combination of all of these. So inductors are easy. For Henry 20, 12, 10, 7 Henry, and 8 Henry. So what do we have? Plus 12 plus 10. So that's equivalent to 42 Henry. Now what do we have here? I have 7 Henry in parallel with 42 Henry. Does all of that? You have four plus 6 plus 8 equals 18 Henry. Okay. Okay, one more example. For this circuit, I of t is given. So that's the total current, I of t. It says if I2 of 0, we know what is I2. I2 is the current flowing in the 12 Henry. I2 of 0 is given. We want to find A and B and C. Okay, let's take it one step at a time. Have here I1, and I2. Now, we know what is the equation for I. I of t is equal to 4 times 2 minus e to the minus 10t in milliamps. Okay, that's this current. We want to find I1 add 0. Okay, 0 minus I2 of 0. Okay. E to the power 0, 1. So that's equal. So I of 0 here, that's 4 million. Right? Equals 4 minus. So what's the equation? That's equal to L di dt. That's the general equation. Okay. 2. That therefore L di dt is going to give you across that integer, which is this inductor. How do I do that? Can I reduce this of parallel and it will be an inductance of 5 Henry. So you have to be careful. Say V equals L di dt. You have to know which L, which I will give. This current up here, which is 4 times 2 minus e to the minus 10t. And be careful, this is in milliamps. So what you have, the 4 can come out here, you have 20. And then d by dt of 2, that's nothing. And then you have here minus sign and d by dt of e to the negative 10t. That's e to the negative 10t multiplied by negative 10. And all of that is in milli, right? I have a milli here. So that's equal to the minus sign and the minus sign are going to cancel each other. I have 200 e to the negative 10t millivolts, which is equal to 0.2 e to the minus 10t volts. Okay, so now I got V of t. Now I need to find V1 of t and V2 of t. Now V1 of t is easy. That's actually this voltage here, across from the 2 Henry. That's given on the circuit in the slide. So V1 of t equals this L, which is 2. di dt is the same current I. So it's d by dt 4 times 2 minus e to the negative 10t. And again, it's going to be in milli, right? So you can do that to find V1 of t. So I got V1 of t. How much is V2 of t? Henry and the 12 Henry are in parallel, and that's why there is only one voltage across both of them, which is V2 of t. But I want to find the value of V2 of t. I have V1 of t. Yes. So V is equal to V1 plus V2. So that's how you're gonna get V2 of t minus V1 of t. It's going to be equal to 120 e to the negative 10t in millivolts, or 0.12 e to the negative 10t in volts. Okay, still one more part in that example. I want to find the currents I1 of t and I2 of t. Now, what do we have here? We have V1 of t, we have V2 of t, which is the same applied across both of these inductors. So V2 of t is the same voltage on that 4 Henry and on that 12 Henry. So I have this value of V2 of t, okay? I want to find the current I1 of t equals 1 over L integral from 0 to t v of tau d tau plus I1 of 0. Okay, remember that. That's the initial condition, the initial current. So I1 of t is equal to, the L here is 4. Less than 20 e to the negative 10 t, or tau in this case, plus I1 of 0. I1 of 0 we found this is the one that we found in the beginning, right? And this one is 5 milliamps. So plus 5. And this is in milli. I'll do this integration. It is 10, and my limits are from negative 10t minus e plus 5. So here I have minus 3 e to the negative 10t minus 1 plus 5 milliamps. That's equal to 3 minus 3e to the negative 10t plus 5 milliamps. So I have here plus 5 and plus 3. So I'm getting 8 minus 3e to the negative 10t milliamps. Okay, so I know there's some math here. One of t and then that's a given. You could say there's another way to do that. We could do a KCL on the original circuit. Because this is the total current I of t. I have here I1 of t, and here I have I2 of t. So I2 of t is equal to I of t minus I1 of t. So both of these are valid and should give you the same solution. Okay? Do we have sound now? Do we? Okay. Chapter 7. Okay, something else is not working here. Okay. Okay. We have chapter 7 now. Okay, good. Okay, so chapter 7 is really an extension of chapter 6. We're going to continue working with inductors and capacitors within circuits. Like you're going to have a circuit where you have sources and resistors and inductors and capacitors all together. We're going to study what we call first order circuits. Okay, so I'm sorry you don't have the slides now. Just try to take notes as much as you can. And I'm going to have them up shortly. So in this particular chapter, we have two types of circuits. Number one, what we call an RC circuit, where the circuit is made up of some resistors and capacitors, or usually the capacitors are reduced to only one capacitor. I mean, if you have two in parallel or two in series, that's fine, you can take them together, but eventually your circuit is going to be made up of only one capacitor and some resistors. And the second type of circuits is a circuit where you have resistors and an inductor. So in this chapter, we're not going to be looking at circuits which have resistors, inductors, and capacitors together. I know we already solved one of those problems, but we solved it only at DC, and DC is easy because capacitors are considered to be open circuit, inductors are considered to be short circuit, so it kind of reduces the size of the problem. But in here in chapter 7, and then later on in chapter 8, we're going to be dealing with circuits that have sources, resistors, inductors, and or capacitors where we don't have DC conditions. Okay. So a first order circuit sorry, 1 second. What's the definition of a first order circuit? I'm going to see that here. A first order circuit is characterized by a first order differential equation. Okay, so I know that you all love differential equations, so that should be good. We have here circuits that are characterized by a first order differential equation. And it's obvious that we should have some kind of differential equations because of the nature of the voltage current relationship for capacitors and inductors. You know, when you have V equals L di dt or I equals C dV dt, that's the basis for forming differential equations. So here we're talking about first order differential equations, and we call these circuits first order circuits. So to have a first order differential equation, you're going to only have to have either a capacitor or an inductor, but not both together. If you have both together in a circuit, you're going to end up having a second order equation. And that's going to be chapter 8. Okay, so here we're saying that the source-free RC circuit occurs, well, the book divides this chapter into what they call source-free circuits and then other circuits where they have what we call a forced response. So here first we're saying what is a source-free RC circuit? A source-free RC circuit occurs when its DC source is suddenly disconnected. So let's say you have a source there that produced a distribution of voltages and currents, and then you suddenly disconnect the source. So you end up having a new situation where you have a resistor and a capacitor, an RC circuit, but there is no source in the circuit. Now, if we only had resistors, we wouldn't have a problem. If you disconnect the source, then suddenly all voltages and currents would just kind of vanish from your circuit. There would be nothing. But here we have a situation where we have a capacitor, and we discussed already the fact that capacitors are energy storage elements. So the capacitor would have stored some energy. And now I am disconnecting the source, and I have here this circuit where I have an R and a C. And we're assuming that the capacitor C had some value of charge stored inside of itself. Okay, so there is energy stored in it. So there's going to be some dynamic now in that circuit. Even though I don't have a source, I do have some energy which is going to produce some distribution of voltages and currents. This is what we call a source-free RC circuit. So the energy already stored in the capacitor is released to the resistor. Do you see that? Remember when I told you that if you have a capacitor in a circuit, at some point in time, it can take energy and store it within itself, within the capacitor. And that's why we call it an energy storage element. But then there may be situations where this energy is going to be released to the rest of the circuit. So here you have that situation. If the capacitor was originally charged, and here we're saying it is charged at time t equals 0, it had a value of voltage across it equal to V naught. If a capacitor has a voltage, it means it has energy, right? Energy is half CV squared. So there's energy inside the capacitor. Now, if you leave it like that, this energy is going to be transferred from the capacitor to the resistor. What's the resistor going to do with that energy? Just dissipate it, exactly. Okay? So we're going to study this phenomenon, what we call the first order source-free RC circuit, where you have a capacitor that had been charged to a certain voltage because of the presence of a source. And when that source is now disconnected, this charge inside the capacitor is going to start to flow in the circuit. And as it goes to the resistor is going to dissipate it. So it's going to die out eventually, but we're going to study this phenomenon. So we say that V of 0 at time t equals 0 is equal to V naught. That's your initial status, initial condition. A capacitor which had a voltage of V naught or V0. Okay, so here's the situation. Initial voltage is V of 0 is V naught. That's the initial voltage. And you'll notice that this voltage is the same across the resistor as well, because look at the capacitor and the resistor, the way they're connected. You only have two nodes, a top node and a bottom node. And the capacitor is connected across these two nodes. So I have this value of V naught across the capacitor, and it's the same value of V naught across your resistor. That's the initial voltage, V of 0. Now, the energy stored inside the capacitor is energy W of 0, or at time t equals 0, is half CV squared, and the voltage being V naught, so it's half CV naught squared. That's how much energy I have stored now. Now we're starting to see what's going to happen. We're assuming that we have a current IC flowing in that direction, and a current IR flowing through the resistor in that particular direction. And both IC and IR are placed in the direction of according to the passive sign convention. Now, if you look at the voltage plus minus, therefore both currents are assumed to be according to the passive sign convention. If you do a KCL at the top node, so IC plus IR equals 0, right? Okay. let's see how we rewrite that. IC is equal to C dV dt. That's the equation for the voltage across your, sorry, the current through your capacitor in terms of the voltage. IC equals C dV dt. And IR, Ohm's law, IR equals V over R. So KCL, which says IC plus IR equals 0, here tells us C dV dt plus V over R equals 0. Okay, so we have an equation here. That's the differential equation, right? If you divide by C, you end up having dV dt plus V over RC equals 0. That's a first order differential equation. So that's what we said earlier, that a first order circuit is described by a first order differential equation, and here you have it. Differential equations, that's not part of our course. You should go back to your math and see how we solve that. The solution for such an equation, V of t, takes the form constant A times e to the negative t over RC. That's how we solve a differential equation like that. That's the form of this solution. Okay? Now we know that at t equals 0, V of 0 is V naught. So let's use that in that solution. You're going to plug in there V of t equals V naught at t equals 0. If you solve that, you find that the constant A that we used has to be equal to V naught. So that would be the solution that you have here. V of t is equal to V naught e to the negative t over RC. That's the solution to this particular first order circuit. It's called the circuit's natural response. What do we mean by natural response? It means it's the response that's produced within that circuit when it's left to itself. We had some kind of source that caused the capacitor to be charged all the way up to a value of V naught, and then we rearranged the circuit. Maybe we flipped a switch, we disconnected the source somehow, and this circuit, when it's left to itself, it has what we call a natural response. Now look at that. We're talking about the voltage, right? V of t. See in the circuit where is V of t? It's the voltage difference between the top node and ground. That's V. Look at this equation here. V equals V naught e to the negative t over RC. We need to understand how that goes, this particular type of equation. I'm going to put it here. V of t equals V naught e to the negative t over RC. And let's see what happens at starting from t greater than or equal to 0. So look at the graph here. Horizontal axis is time. Vertical axis is this equation, V of t. And at t equals 0, that's the beginning point when we're starting to look at this behavior. The voltage was equal to V naught. That's the initial voltage that was across your capacitor. If you want to plot this response, it's going to look like that. Okay. So this is this equation, V naught e to the negative t over RC, the natural response of an RC circuit. And this product of R times C is called the time constant. And we refer to it as tau. It has units of time. If you multiply R in ohm times C, which is the capacitance in farads, and you go back to week 1 when we had that table which puts everything in terms of the initial units for the Système International, then you get R multiplied by C is going to have units of time. That's why we call this a product a time constant. So look at that. Your capacitor and your resistor connected across it had one and the same voltage across them, which started off by being equal to V naught at time t equals 0. When it's left to itself, this value of voltage is going to decay. You see that? It's called an exponential decay. It's going to go down with time. And after some time, it's going to completely vanish. You won't have anything anymore. So this energy stored inside your capacitor, which kind of displayed itself in terms of some voltage there, it's going to keep decreasing with time. So the energy inside the capacitor is going to vanish. Where did it go? Well, practically it flowed, it created this current IR, and IR through the resistor is going to dissipate some energy, right? I squared R gives you power that's taken out of the circuit as heat, and therefore this voltage is going to decrease. So this is what we call the natural response. I'm going to stop here. I'm going to post this, and then next week we're going to look in more detail at that particular equation, because we're going to try to understand this exponential decay. It has some features that are interesting to know. Yes? Yes, thank you for asking. Now, several people have asked, and I mentioned it before, I'm going to mention it again. The midterm is covering all the way up to the end of chapter 5. Okay, so chapter 6 is not part of the midterm. End of chapter 5, the midterm is about an hour and a half. And I told it starts at 10 a.m. on Saturday. Okay, so I already said that. And I asked for a room to be booked. For some reason, they sent me a wrong room number. So I asked for, clarification. Please tell me again which room number it is. So I received an answer that says, oh, sorry, that was a typo. The room number is probably either this one or the one at the end of the corridor. Okay, so I'm gonna, assume that it is 2529, which is the one where you had the quiz at the end of the corridor, or this room. Either way, just come here. The midterm is gonna be here. Okay. Okay. Another question? Formula sheet. Yes, there's going to be a formula sheet, and I'm going to post the formula sheet beforehand. I'm going to post it today. So you would know what to expect. You would know what are the formulas that you're going to have with you in the exam. Okay? Not too many formulas. I mean, just some equations about, what's Ohm's law, KCL, KVL, stuff like that. You should know that stuff. If you spend any time at all solving some problems, you wouldn't really need a formula sheet. I'm still going to give you some of the main formulas. Any other questions? Yes? Yes, I'm going to post the answers for the problem sets all the way up to chapter 5. I'm going to do that as well. Okay, thank you very much, and I'll see you on Saturday at 10.